for 9 to this exact pattern for 9. This is saying, how can I differentiate 9 from 8, from 1, from 0, right? So I need now sufficient features and sufficient characteristics of the system in order to be able to differentiate those elements. But where are the features actually occurring in this space? What we're used to from our perspective of what a feature is, we've been doing a lot of feature engineering. Natural traditional machine learning processes require us to develop our understanding of the world by extraction of quantified reality, right? I measure your opinions, I measure your behavior, I measure your physical characteristics, and then I assign you as a person or object into a category based upon those characteristics. This system attempts to do that process from what would effectively be raw input from a certain perspective, okay? Now that is typically a step above whenever it comes to strictly binarized image input with respect to something like a vectorized network, because if you think about it from this perspective, at one point in the system here, right, that is at a higher point in the vector array than the next subsequent element connected to it. So if we were to think about drawing our 9, what elements do we have of the 9, right? We've got some sort of surface or plane moving in this direction, right? We've got an arc moving in this direction, an arc in the bottom section, right? There's a lot of feature characteristics that make up the number. But as I said previously, we're going to vectorize it such that this becomes one line sequence of the vector. So this portion here, right, if I was to look at it like this, right, this portion here is here, and then this portion here is down here as well, right? So in truth, their connectivity with respect to this system, the presence of the connectivity in the system is a little bit hard to differentiate with respect to the spatial characteristics. Since I haven't provided this system with a knowledge of what the width characteristic is expected to be, right? Because when I draw it based upon this vector, I'm composing it based upon a known width. I'm cutting it up in these width division chunks. What I'm feeding it in as pure activation numbers, these elements, as noted, can be disjoint from one another in such a way that they don't adequately or adaptively describe that underlying system, at least not in the way we think of when we think about human characteristics, right? We tend to think about things with regard to spatial chunks. We describe the characteristics as the items relate to one another within space. So part of the way in which novel systems within the last 5 to 6 years have been doing this is a departure from the traditional neural network framework. I'm starting off the traditional neural network framework, and I'm going to try to actually fix some of the problems that this has within it. So I'm showing you the system classifying image data, which is really problematic because for a long time, how many of you understand that we've really only had Google image search for like 8 years?
Right? More than 8 years, I think.
About 8 years.
Okay.
All right, so 8 or 9 years. 2014 was the first time that we really started seeing large-scale convolutional neural networks utilizing image-based search mechanism, right? So correlating image-to-image systems. There have been attempts to implement it in like 2012, 2013, large systems like Watson and other intercorrelates. They used field systems and nodal connectivity and graph networks in order to try to create similarity between elements, but they did not work at high resolutions, all right? They did not work if the images was slightly misaligned, right? So if you rotated the image slightly, the system would stop being able to recognize it. So if you wrote this 9, right, you wrote this 9, and this 9, and this 9, and this 9, right? All of those were effectively considered as slightly different things, right? They're slightly different images. I might be able to correlate to one or the other correlatively, but their intercorrelation with respect to one another was not easily done because there were dissimilarities between the original items. Notice also this 9, right, because it's so much larger than these, would have a different scale characteristic. So creating scale invariant systems such that I can recognize this 9 and this 9 and this one and this little one here, right? And that they're all the same thing. That's a characteristic of a a scale invariant system, which we have not yet fully recognized, but we will talk about here in just a little bit, all right? So this encapsulates and contains the image, but we know that 9 has to be big enough in order to be able to be adequately described by the system. I'll show you guys how this is done with something called a convolutional neural network before we get done with what we're doing, but it'll probably take us part of this week or if this week to be able to do it. Because I would rather make sure I get through this material, right? And then we can go back and we can do the other stuff. It's interesting. I think I'm going to put some of the context of some of the things we're building here. And you guys will see the reason why some of these other methods are good and don't cost as much. So I put this particular element here in place because when we feed forward into the next system, when we talk about generalized additive models and neural networks are like this, right? They have a lot in common with one another. So we're going to build back and forth between those a little bit as I talk about neural networks and talk a little bit about GAMs and neural networks. Those are going to go together, right? Why I say that the generalized additive model and the neural network effectively have some unification is that neural networks use piecewise parts of a decomposition of the system. Instead of utilizing strict edge functions on the operation, they use weighted recombinations, okay? So we remember what we had said previously, that any system of inputs times weights is effectively a linear, right? So what is this? Z is a multilinear regression. Nothing new. But notations change slightly because of the fact that we now have this characterization of alpha, right? What does alpha represent? Alpha represents some operative characteristic of Z, okay? So alpha is actually going to be the output of the system. We're going to have some alpha, which we're going to call input as well. There's a reason why, because if you remember, neurons connect to each other, right? So you have dendrites on both ends. You have effectively look at it from the perspective of leaves on a tree, right? You have the trunk bringing everything together, and then you have the roots at the bottom, right? You think about it from the perspective of the roots are sort of pulling everything from the natural world, they're bringing it up through the trunk, and then they're putting it out at the limbs. Another tree, another neuron sets with its roots attached to the leaves of the previous tree, and then you have sequences, you have links, cascade, bucket chains, where this tree brings things out of this space, this other tree propagates it to the next one, that one propagates to the next one, right? Each one of them gets to have the integration, meaning that it is connected to all of the people that it is listening to, all right? So neurons aren't exclusively hooked up to one neuron, right? So I'd have neuron, right? I have the output of the system, I have its dendrites, and I can actually have a variety of other neurons hooked up to this one neuron, right? Such that I have multiple individuals that I'm propagating the information to. I also can have multiple neurons that are seeing the natural world, right? Also hooked up to other multiple neurons. So I'm actually getting every single neuron at the subsequent layer is getting all of the neurons it's hooked up to from the previous layer, right? This is a sequence-driven system. Getting this and fully getting the picture of it is going to take a little while of messing with this so that you understand kind of how it works and what it looks like. But I have a really good visualization of it, a really good website for this that we'll look at. I try to get through it today because I want to be able to do that at least once. So the input of a system this is the input vector we were dealing with previously. We're going to, instead of calling them coefficients, all right, we're going to call them weights. There really isn't much different, but the reason why we say weights is, I was talking about this the other day and I got to thinking about it and I remembered a lecture that I had listened to previously. You guys know how tuning forks work, right? So you know those tuning forks that you can set pitch on? Have you ever seen those? Where they've got little weights on the side and you can change where the weights are set to adjust the resonance characteristic of the tuning fork.
Yeah.
All right. These are the weights. All right. We're going to change the resonance characteristics of the system such that we modify which frequencies or which elements that particular neuron is sensitive to. So weights are actually a mechanism for determining or effectively adjusting the relative sensitivity of that neuron to specific types of input. Now, what we call these systems are fully connected networks, meaning that every neuron is connected to every other neuron in the system. So there is going to be a weight present at every connection in the system. But multiplicatively, we start off by taking the inputs times the weights, right? And then we're going to sum that all up according to this value z. We're going to add a bias characteristic to it because we recognize that the system of outputs relative to the scale of the weight system will result in some bias characteristics. So we're going to utilize a linear offset or an intercept in order to compensate for that, right? Now, why this is the bias, is this similar to bias within data set characteristics? Kind of, yes, but it's also a requirement in order to make certain types of decisions. The mean of the outputs of the system has to be accounted for in order to adjust things such that even the normed cluster, right, we now have to offset for the normed cluster. That's effectively what we're looking at, is saying that the weights times the inputs effectively does a zero mean projection, and then we take the bias in order to push it back up so that we can deal with the real world version of the data. We take that z output, right, that's the summation function up there at the top, and then we run it through an activation function. When was the last time we saw these activation values, sigmas? This is logistic regression, okay? We're going to run this through a system, but let me first mention beforehand, I think I have a slide out of order here for what I would like to see, that the activation function is either going to be something like our logistic regression, right? Or as I said previously, I called this a sigmoid. Anybody remember me calling it a sigmoid? The reason why is because of this. Because sigmoid operator refers to a logistic function, right? Or something along the lines of the hyperbolic tangent function, which is utilized. The one thing that's nice about this is, similarly to what we were using for a logistic function beforehand, is that I now have a multilinearity, right? And what does this really look like? This looks like a multilinear regression feeding into becoming part of a logistic classifier, or logistic output function. I'm effectively classifying every single set of inputs and weights. I'm classifying, I'm creating the differentiation, right? So I said first I integrate sigma, right? I take capital sigma, and then I differentiate this small sigma, right? Or the differential function. This is going to lead to an output A again. Interesting. Why did I use A on both ends? Well, as I said previously, it's the same A. It's still an activation, right? The neuron is initially activated on its input side. Something comes up, flicks it, right? Pushes against it. Some photon hits it. It's activated at that region. The degree to which it's activated for each individual element that is connected to within the region is going to be adjusted based upon its desired sensitivity. You get more or less sensitive based upon how you turn that weight up or down. You can actually have positive or negative weights, right? You can become potentiated, that's where you amplify it, that's where you multiply it by a value, a positive weight, or you can inhibit it, in which you multiply it by a negative weight, where you see a red flag, right? Where you see a counter indicator, an opposite of the direction you'd like to have, okay? The combination of all of these elements together effectively turns the neuron into a little miniature pattern recognition system. Effectively based upon whatever a number of elements the system is bringing in, it tries to find a specific set of pattern elements within that data input. That is meaning effectively saying that it is going to create one system of the best relative linear classifier to separate the things that it's interested in from the things that it's not interested in. So every single individual neuron in an artificial neuron system, which we also call a perceptron, will be a creator of its own little linear classifier, its own little linear spatial classifier for the inputs it's been provided with. Now, what does that do us? We know linear classifiers weren't all that powerful, so we didn't really utilize them that much. But when we use more of them, we get up to something that gets to be really cool, all right? This is where we start talking about that the idea of the hidden layer within a system is where the input system times a series of weights and activations become the input of the subsequent layer, right? And then those elements are effectively the features of the neurons at the next layer, right? So features from the natural world become activations. Those activations become inputs for the next layer, right? Those features are processed and those become outputs for the subsequent layer. So you have a group of individuals who are looking at something, right? Each one of them raises their hand relative to whether or not they see the thing they're interested in. We effectively treat those as the features that we're going to utilize at the next sequence of the system. So neural networks are feature extraction methodologies in the effect that they try to find likely correlates and likely sequences of values from each layer, right? Utilizing each layer's output as their input. So each layer utilizes the previous layer's output as its relative input, and does so, and as I said previously, in a fully connected way, such that every single element of the hidden network is connected to every single element of the previous layer of the system. Now, the only way in which we can accomplish truly complex systems is by this process of hidden layers, and we'll talk about it in a bit. But we have sequences of weights and biases. We're already very familiar with this. We have activation functions. Those are our logistics. And then we pass those elements off to operatives. Now, what does this ultimately end up creating? Even for a relatively simple system like this one, 3-dimensional input, 4-dimensional hidden layer, and 2-dimensional output, we have 26 learnable parameters. That is an incredibly high flexibility network. I have 26 parameters, 26 individual adjustable characteristics of this model to try to be able to adapt it to the system of interaction between those 3 original inputs and those 2 outputs. Anybody think we're going to run into some curves of dimensionality and some overfitting characteristics pretty quick? Absolutely. Absolutely, all right? So we have a lot of the stuff we do is to try to offset and characterize for that problem. But here's another thing that we do that's very interesting with respect to the way this system works is that artificial neural networks, you don't sit down and read an entire book or read an entire library and then move on with your life, right? That's not how life works. You don't go and try to amass all relevant data. You go and you live. You exist in a natural adaptive state, meaning that you take in information, you adjust your behavior characteristics, and you try to model what's going on underneath the surface. Previously, we had tried to fix the best solution, the ideal solution, the perfect convergent solution from the relatively infinite search space that was available with regressions. We came up with ideal cases for best F-hat fit. Instead of that, however, we're going to treat neural networks by working with small sequences or batches of information, right? We're going to watch for a while, we're going to make some assessments, we're going to see what our error was, and then we're going to go back and we're going to adjust this system, this assessment, in order to try to create a better convergence between our inputs and our outputs. This is the idea of a sequential learning or adaptive update learning system. Right? Not all models are done this way, but we simulate the process of the thing living in an adaptive world during its training process by feeding it a small amount of samples and then having it adjust its understanding of the system based upon its previous experience, that is its stored weights, and all the new samples that it's seen during that particular epoch of the training process. So we can update a model, we can train a model with a small number of samples, and then retrain it or effectively help it learn more by showing it more samples, a little at a time, until it converges to a realistic solution. This is the interesting part about it, is we're trying to get it to stop before it overfits. So if I don't show it everything at once and let it converge to absolute best solution, by only showing it a small portion or a small window of the likely inputs of the system, it doesn't actually see everything at once. And in a similar way to k-fold methodology, sort of blocks off some of the remainder samples, it can't adapt to everything at once, right? It can't memorize the training set. Now, it will eventually be able to effectively memorize it by having the samples that it's being shown coming through it over and over again, right? It will converge to an optimal output. But what we tend to say is that the system will converge ideally. All right, so let me show you something real quick. I'm going to click ahead real quick. There's some examples in here of actual runtimes of how the network is calculating. We can talk about those a bit. Come on, get past this. Where is that at? Oh, this is dumb. Sorry, give me a second. Oh, here we go. Sorry, it's way further than I thought it was. Yeah, I want to show you just real quick how this operates and some of the basic characteristics of it. So we've seen previously these sort of strict classification networks, right? Where we only need, realistically, we only need just one regression input. Now, if I have a nice, easily separated set of elements, how would I normally construct this? Probably like an LDA, right? So let's see how long it takes this system to converge to an understanding of an ideal output. It started to create a system. I'm going to go ahead and discretize it so we can see it as a strict understanding. We saw that we had a decrease in test loss, right? Test loss went down, trending loss went down. Let's go to the next system. I'm going to show it a few more samples, right? Showed a few more samples, a few more. Notice what's happening. We're starting to converge to a realistic minimum level. Now, when these are well separated like this, what do we think is going to happen? Effectively, this will go zero, right? Why? Because it's fully separable, right? So when it's fully separable, yes, you can actually have a perfect regression, all right? Would you ever use a machine learning task to solve something like this?
No.
No, because it's so easy to solve. You just need a threshold, right? Just threshold of activation, okay? This is a far too complex mechanism to solve this process in most circumstances. However, we know that there are very few free parameters here. How many do we have? We have one weight, two weight, and then one weighted output as combining those two elements together into this little slant neuron here, right? So we have the measurements in the y-axis, measurements in x-axis, characteristic for spreads, and then we're going to recombine them together with the linearity. Now, I'm going to change some stuff. I'm going to add some noise to this system, such that I'm going to mix these items together pretty heavily. Notice what happened there. What happens whenever I start to run this? Notice something. I'm not going to get down to that zero value anymore. Why? It's just not possible. In the same way that it wasn't beforehand because of the RSS of the system, right? There's residual error. Am I doing the calculation of error any differently than was previously? No, I'm not. This is the same mechanism. This is an RSS-driven error or MSE-driven error, all right? Notice it's hit an absolute minimum. Now, what's one of the things that might be holding me back in this case? Well, I only have one linearity, right? I'm just effectively saying I want a one-dimensional system in order to be able to separate the surface as something that might have a slightly higher dimensionality. Where's my training error, right? Notice, training loss is 0.126. Where's my test? 0.137. They're different than one another. They haven't significantly diverged yet. So let me show you the test data real quick, all right? That's the test data projected on top of it, right? Training, testing data. We see that some of the reasons why, like these two blues up here on the edges, these oranges on the edges here, might be an indication that the reason for those specific level of testing error is what? We have samples that are in the testing that are in a region that doesn't seem to be reflected by a similar distribution in the training data, right? So notice here, there's two oranges in the testing data that aren't present in the training data. So that characteristic is going to add to the additional testing loss because we now have samples that aren't represented for the spatial distribution characteristic of the system. So I want to go ahead and increase the complexity of this system. I'm going to add a couple additional neurons, and I'm going to let the system attempt to train for the surface that's happening now. I thought I said they were linearities. That doesn't look like a linearity anymore, does it? Huh. How does that work? This is the really cool part of neural networks. Despite the fact that every individual activation is a linear surface, region to region, element to element, spatially, each individual neuron's activation can be reassigned by a weighting process to that output. You remember previously I had a characteristic where I talked about the idea if I had a second degree system and a first degree system, if I recombine this by addition, I would end up with something like a semi-curvature process. Let's say that instead I actually want to monitor the curvature process here at the top. How could I do this with the linearity? Linearity in this surface, this surface, this surface, this surface, this surface, right? Treating them only as the elements that are concerned with the regions of interest for the combined surface, right? So it is just the element, or just the straight line element, that makes up the intersection with the outside of the surface. I'm effectively treating a surface as what? Recombinations, weighted recombinations of linearities. What do I mean by weighted? I mean, for this region, from here to here, I use this one. From here to here, I use this one. From here to here, I use this one, right? Etc. So by weighting them, by saying which one I use in which area relative to the input of the system, I can create strange recombinations of the surface such that individual systems can be reweighted together to be able to create more complex elements. If I add an additional layer to the system, and I add a couple additional neurons, this system will have a lot of complexity, such that it will, maybe if I crank down the, we actually need to turn this up a little bit. Yeah. It's gonna try to fit to that, but it's not gonna do very well, because it didn't start very well. That's a little bit too complex. I was trying to actually go a little bit the opposite direction. So eventually this system will start to converge. I think it might be because of the activation type. Eventually this system might attempt to try to converge by capture those outputs. So at the moment, I don't really have enough input features. There we go. It's going to try to attempt to converge to that output system, but it's not doing so because it's not well offset. But let's take into consideration this value, right? So let's start off with a less noise version of it. Let's start off by saying only one hidden layer. All right, so we have 1 minute left here. Only one hidden layer. Notice, what do I have with this system? I have a circle in the middle with blue and a circle on the outside with orange. What's going to happen with only a single neuron? Nothing. You won't be able to converge. Why? Because there's a nonlinear characteristic here. What if I increase the number of neurons in the center layer? I only need more external complexity. What has been created? How did this create a square in the center? Right, I'm going to show you the non-discretized output so we can see how this looks. This is that edge surface, that edge surface, that edge surface. All right. Notice they're reweighted. They're adding them together with a certain configuration or a certain amount of each of these linear surfaces. By recombining each of those linear surfaces with a certain offset from one another, I now have a region bound inside of that orange circle drawn by a series of linearities. If I keep adding additional elements to the neuron layer in the center, what do I end up getting? A slightly more complex edge surface. The more of these I put in play, the rounder it gets. Why? Because each individual one is contributing to a certain regional surface by the recombination of elements. Is it a direct visual version of that? Not exactly, all right? But it is very similar to it when you think about how the recombination works, because here we have a couple of things that we didn't think about. Each one can be biased, right? And each one can be rescaled. So the original decision surfaces can be biased and rescaled, reconfigured, put back together, right? These initial features become these features, which become processed by this system to create this recombination that results in a separability between things that were not linearly separable by recombination of linear elements. Right? This interfaces with that generalized additive model framework. That's more the GAN system, where you take regional considerations of different linear or nonlinear activations. This is the neural network operation version of the system. Right? We will do a lab with this. You guys will get a chance to play around this TensorFlow Playgrounds website, and I'll upload the slides for today so you can look at it as well. But we're going to keep looking at and keep playing with neural networks as we go through this week, and you guys get to see what kind of really cool stuff happens. All right? They're a big hammer, like a lot of other things, as I've said beforehand. When you have a hammer, everything looks like a nail, right? So AI is a really big hammer. So everything, you start to walk around and go, oh, I can do that with this, I can do that with this, you know? And you're swatting flies with a nuclear weapon after a while, right, okay? Because these systems get so big and so complex, and it's like, yeah. So let's remember that the basic things we learn still have a lot of value and a lot of merit, because they can help us solve basic systems where too much complexity actually occurs. But neural networks can solve problems that we didn't know we could solve previously, and they do so in such an automated way that we don't really have to figure out a lot of the internal parameters for it. We just have to figure out how many neurons or what element of the layer the system needs in order to be able to create the minimum degree of separability for the surfaces we're interested in. So yeah, thanks guys, I'll talk to you on Wednesday.
Thank you.